So let's talk about distribution of log events in microservices by leveraging Apache Kafka capabilities. And this is an extension of previous video series regarding distributed API systems, and you can check out the previous videos related to this. And let's get started. So according to the agenda, we will first walk through the design which is related to this video and how to log messages directly onto the Kafka, and let's talk about the subpub pattern, and then a detailed discussion about Kafka internal capabilities since it is a kind of a real implementation of a subpub pattern. We'll talk about topics and partitions, the role of Zookeeper, publisher, consumer and consumer group, and finally a little bit about streams. And then we will talk about factors to be considered when we are going to monitor the Kafka in production environment. And finally, I will walk through the practical demo of this design with a code walkthrough at the end of this video. So we have discussed details of trips and car microservices, and you can watch previous videos related to this. So talking about logging, there are two main streams of log event distribution from each microservice as per this example. One, which is in green color, is for analytics purposes, where log events could be written onto Logstash, which will get indexed on Elasticsearch and ultimately displayed over Kibana dashboard. And this is an async eventing approach, and we will discuss details about the async logging data in this video. And the other stream in blue color is for handling specific errors generated to the user with a specific error code for further troubleshooting. And it is vital that we do not lost any error messages dispatched to the end user. And those service errors are splitted into different logs such as error code based and geo based. So you can assign specific error codes to a specific team or specific monitoring teams. And on the other hand, errors could be splitted into geo based event streams, where based on event log time, it could be assigned to a currently available team or specific system for further troubleshooting. Let's talk about analytics workflow. So there are 6 different log levels, and for this we will be selecting info as a log level. So warn, severe, fatal, error logs will get printed along with the info logs. I am using SLF4J API in here, and it is a log implementation independent approach where one can use logback, log4j or any other logger implementation, and here I am using log4j2 as my implementation. And log4j2 has different appenders, and the Kafka appender will directly publish messages onto a configured Kafka topic. And log4j2 can execute appenders in async nature, like messages will get buffered and dispatched. And you need to configure this buffer based on your predicted throughput. And this appender will publish messages onto this Kafka cluster, and we will see the implementation related to this at the end of this video. So on the service error workflow, I will be directly publishing this error payload onto Kafka cluster, since the workflow is for specific error codes, and this is the error ID and this is the specific error code that I am talking about. And this Kafka publisher is a remote dependency for microservices. So the main intention is to reduce the unnecessary boilerplate adding on to each and every microservice. So all the microservices can share Kafka producer from one common implementation with the necessary configurations. And another approach to handle this is that we can use a sidecar pattern for this, where you will have a business process running in the same container with a sidecar, and especially if you are deploying in a containerized environment. So there are a few advantages, like decouple logging aspect from the business logic. So since the logging implementation is decoupled, the logging workflow could change without impacting business process. So there are a few negatives also, like this will increase complexity of the solution, and you need to ensure sidecar is available all the time. So decide to have this sort of implementation if you are running with a large number of microservices in a service mesh like environment. Then you can gain some other advantages also, like microservice communication and especially the ability of monitoring the services. This is an async messaging pattern where the publisher will publish messages onto event queue or a log of messages, and the subscribers will poll for messages, maybe with short polling or long polling. And the benefit is the subscribers can add or remove without any intention of the publisher, and Kafka is known as a popular implementation of this pattern, where it is maintaining a log of events in a message format with indexing which is called as offset. Let's see how the synchronous communication works and why it is not suitable for distributed log eventing workflows. We have these two services communicate with each other under the same rate and all going good under low throughput. So what if the processing rates are different and microservices starts to scale up? Then the publishing service will have to wait until consumer respond message acknowledgement, which is generally known as a blocking IO operation. And on the consumer end, the back pressure will get increased and sometimes it may not even be able to consume the messages in the same rate. So there could be potential data loss, and this could solve with client side load balancing, implementing service discovery and having circuit breakers to handle overloads. However, it will incur additional infrastructure cost, and if synchronous is the only option you have to follow, use a synchronous workflow, else these problems could be solved with the asynchronous workflow. So let's talk about Kafka and its capabilities in detail. Kafka originally invented from LinkedIn, and as we discussed, it is an implementation of pub/sub pattern, and it is more suitable to call as a log of messages instead of a queue, and it is a persistent log. Since it is persistent, even after fetching a message, it will available on the log for later retrieval. And the log is composed of topics, and the topics are composed of partitions, and we will discuss details of it later. And this is complying with the eventual consistency model, where we will have a leader who handles all the write operations and followers sync messages from the leader to be in sync with the leader. Partition tolerance. So if we lose any node with containing partitions, it will neither affect on the consistency of the system nor lost any of the data. So looking at the Kafka cluster from 30,000 feet above, it looks like this, and it is composed of message brokers, which are actual independent servers, and each server identified with a particular IP address, and it has a particular port. And we have a publisher who is also known as a producer in Kafka world, who is sending messages, and the consumer who will be subscribing messages from the Kafka cluster. So as we talked before, the messages are stored in topics and they are distributed across brokers within the cluster. And this topic is a data container, and a particular broker can have multiple number of topics. So what if a node goes down? Did we lose data of the partitions as per this example? It's not the case. The Kafka topics are containers for partitions. In other words, collection of partitions compose a topic. So topic A is splitted into 6 partitions as per this example, and they are splitted onto 2 brokers, broker 1 and broker 2. Now what if a particular node goes down? Still we are losing a part of data in this particular topic. So how Kafka addresses this? Kafka partitions are replicated across multiple nodes. As you can see here, the first 3 partitions 0, 1, 2 are replicated into broker 3, and 3, 4 and 6 partitions in broker 2 are replicated into broker 4. And those partitions and number of replicas are decided at the time of creating a particular topic. So now what if we lose a particular broker? So even after particular broker failure, we do have backup of this particular partitions in broker 4. So entire topic A data is retained within the cluster without any impact. So let's look at the Kafka cluster with a descriptive example. Here I have a 6 broker setup of this cluster, and let's say we have only one particular topic, and it has 4 partitions like 0 in red and 1 in blue, 2 in yellow and 3 in green. As you noticed, each partition is replicated to 3 nodes. So when I am creating a Kafka topic, I need to define the number of partitions I want to maintain, which is 4 as per this example, and the replication factor of each partition has to be defined. So as per this example, the replication factor is 3. And according to CAP theorem, Kafka is partition tolerance with eventual consistency. And you can see each partition has a leader and set of followers. So who maintain the partitions, specifically leaders and followers, and who maintain the node and the partition assignment metadata. For that we have a special node appointed called Kafka controller. Kafka controller could be any of the broker, and it is continuously watching for broker failures. And in the event of broker failure, it will appoint a new leader for failed partition. And the controller metadata are stored externally, because in case a Kafka controller goes down, we will lose all the partition assignment metadata within the Kafka cluster. So who appoint the Kafka controller and who maintains the metadata of a particular controller? This is where the Zookeeper comes into the picture. Zookeeper maintains all metadata of Kafka controller and takes the responsibility of appointing a new controller in the event of failure. Talking more about Zookeeper, it is originated from Yahoo, and Kafka uses Zookeeper to store all cluster metadata. And it is stored data in a tree-like hierarchical data structure where a key value pair is created as a particular node. So talking about overall use of Zookeeper in Kafka ecosystem, it does the controller broker election and it maintains a list of active brokers at a particular given time, and it keeps all cluster metadata like partitions and their assigned brokers. Then it does access controlling of Kafka with read-write coordinating and with maintaining the offset, which is known as the index. Further, it can maintain quotas based on the broker configuration where it decides message consumption by specific users. Let's talk more about Zookeeper. Zookeeper composed of a group of active Zookeeper servers which is known as the ensemble. Same as Kafka, Zookeeper has a leader node and set of follower nodes. And there is a distinct difference in data nodes where the persistent nodes keep the data even after Zookeeper cluster restart, but the ephemeral data will retain until the data creator stays alive. And if the data creator goes down, ephemeral data will get lost. Kafka used this behavior to appoint and maintain Kafka controller. So the Kafka controller is an ephemeral node, and in the event of controller failure, the Zookeeper will delete the controller and it will initiate a request to appoint a new controller following the metadata that it has. Let's assume we have a Kafka cluster like this and the Zookeeper cluster without any appointed controller. And let's check out how the controller is getting appointed. Since no controller nodes are available in Zookeeper, all the brokers will attempt to get registered as the controller. The first broker who gets registered as the controller will get appointed by the Zookeeper, and the rest of the brokers will get an error saying node is already existing. So all other brokers will get an update about the controller broker. Especially they will keep the timestamp created with the epoch along with the controller node. So as you can see here, controller node is created with a timestamp from the epoch, so it's a ephemeral node. And we will see how this epoch is used later. And the Zookeeper will start continuous heartbeats with the controller to make sure it is alive. And if you are executing this command on the Zookeeper, then you will be able to get the details of the Kafka controller like this. So in my example, Kafka version is 1, broker ID is 87, and it is given the timestamp. So this is what is used as the epoch. So what if the controller node failed? And this can happen. So the first thing that will happen is the ephemeral node will get removed. As the behavior of ephemeral node, when the creator dies, the node gets deleted. Then the Zookeeper watcher will notify the failure of the Kafka controller to all the other active brokers. Then the same process will get executed, which we discussed earlier, and a new controller will get selected with a new epoch timestamp. So as you can see, it is in blue color. The previous one which was created is in green color, and the new epoch is updated on all the available and active brokers. So what if the obsolete controller broker returns? It might be obsolete due to long garbage collection event, or it may be not reachable due to kind of network delay. Those things can happen. And it does not know anything about the new controller who got appointed with a new epoch. And it will try to write data thinking that it is the controller. And if this happens, it will be kind of a disaster. So this is where the epoch comes into play. So the broker and Zookeeper will validate the request from the controller against the latest epoch. So this is also known as zombie write. So this broker 4 is kind of a zombie. Since the epoch mismatch, then the all writes will decline, and when the zombie node recovered, it will start following the new controller, and after that partition rebalancing will be happening according to the latest broker setup. So let's talk more about Zookeeper. As we talked earlier, Zookeeper cluster composed of multiple Zookeeper nodes, which is known as a C node, and each C node is a kind of an independent active server. And as you can see, each C node is identified by a particular IP address and a port number. And this collection of C nodes is known as a Zookeeper ensemble. And let's look at the primary configuration of a Zookeeper server. Tick time is the basic unit of single tick in milliseconds. So, a single tick will be equal to 2000 milliseconds according to this example. The sync limit specifies how far a follower can be idle from the leader in ticks. The init limit is a timeout in ticks to get connected to a particular leader when a leader election is happened. The data directory holds the cnode metadata, and this client port is a port which is exposed to the Kafka and for CLI based executions. And this admin port is the administrative port of the Znode, and those are the list of servers within the ensemble. As you can see, according to this example, all 3 nodes are listed here. So, each and every C node should have this same configuration. And there are 2 nodes assigned to each server. The port 2888 is used for peer level communications, like if Z nodes needs to agree on a particular update sequence, then they will use port 2888, and the port 3888 port is used in the leader election, and you can change those ports based on your requirement, and we will talk more about Zookeeper leader election later. So, out of all Z nodes at a given time, one node will get appointed as a leader and the others will follow the leader. The internal protocol used in Zookeeper is known as the Atomic Broadcast Protocol, which elects leader and keep all nodes in sync. And each node has a DB replica to hold internal metadata. And only the leader will get the control of request processor to govern the write operations. The leader and the followers will conduct continuous health checks to maintain the ensemble. So, what if the leader failed in the Zookeeper cluster? So, a leader could fail. Either the leader does not have adequate followers to support the leadership, or the leader is unavailable due to network latency or maybe long garbage collection operation. And the ensemble will enter into the mode to elect a new leader, and the group of nodes take part in election is known as quorum. And there is a specific formula to calculate the quorum and the optimum cluster size. Before that, we will check what is the difference between ensemble and quorum. The ensemble is number of Z nodes in the cluster, and the quorum is the number of healthy Z nodes required to perform a leader election. Q is equal to 2n plus 1 is a formula which is used to decide the number of nodes required to set up a healthy ensemble, and n is the number of nodes which could fail while maintaining the active cluster state. So, according to the quorum formula, if we have one node, none of the failures will build the ensemble, and the 2 nodes also same, nothing could fail, and 3 nodes can establish the healthy cluster allowing 1 node to fail, and the 4 nodes will return the same result as 3, and the even number clusters does not perform healthy ensemble, and the 5 nodes will allow to fail 2 nodes and still maintain a healthy cluster. When setting up infrastructure and quorum, you need to be careful since it could cause the brain split problem. Like if you deploy 2 nodes in one region and other 2 nodes in another region, and if the region communication is failed, the cluster acts as 2 different clusters which will operate abnormally. And the other thing is, too many nodes in the quorum will consume more time to elect a leader. So, be careful about selecting the size of the quorum. So, let us look at the leader election of the Zookeeper. When the leader election is happening, Z nodes exchange messages containing Z node ID and the latest transaction it holds, and each Z node compare received messages with its own latest transaction ID. If the received transaction ID is lesser than the transaction ID a Z node holds, the receiver holds the latest transaction, otherwise the receiver is outdated. And the C node which holds the latest transaction ID becomes the leader naturally. And once after the leader is appointed, the followers start to follow the leader, and the leader starts sending updated transaction to its followers in order to keep all the C nodes in sync. Then the new leader starts heartbeats with the Kafka controller. So, let us talk about producer. A producer will publish messages onto a Kafka cluster on a specific topic. Let us consider the same example that we have taken before with the single topic and with 4 partitions and 3 replicas. And if you look at the producer source code, when you are sending a particular message, you need to provide topic, key and the value as parameters. So by default, data will be written in round robin manner. So the first message will be written into the leader of the 0th partition, and the second message will be written into the leader of the first partition, and the third message onto the leader of the second partition, and the final message will be written into the leader of the third partition. And the special fact related to this is that there is no guarantee of the order of the messages. So the input message order will not be the same as the output message order. And if you want to maintain the sequence of messages delivered, we have to use a partition key. So according to the source code, when sending a particular message, in addition to the topic key and the value, you need to mention the partition key. So each and every time, if you want to maintain the sequence of the messages, then you need to use the same partition key. So what will happen is, all the messages with the same partition key will be written to the same partition. And there are 3 delivery semantics such as at least once, at most once, and exactly once. And it is important that the producer retries will make duplicates. Like in this example, if the producer is failed to get the message written acknowledgement, then the producer will think that the message writing operation has not completed successfully. Then the producer will retry to write the particular message. Then what will happen is, it will ended up creating a duplicate message. So this is also known as the zombie writes. So you need to avoid this sort of scenario. So in order to avoid this problem, you need to use an idempotent producer in order to ensure that you follow exactly once delivery semantic. Let's look at this example. And as you can see, a message sequence is maintained against each producer. And the producer ID is identified by the process, and upon each write, the sequence is updated. And if the sequence is same, it is a duplicate attempt, and the write will be discarded in order to avoid the duplicate. This is how the idempotent producer works. So let's look at consumer capabilities. A given single consumer can read from all the partitions. However, this will slow down reads. And each partition maintains the last read offset by a specific consumer. That way it avoids duplicate reads. And if you execute this command in one of the Kafka broker, it will display the topic and the partition along with the last read offset. A consumer can read the next offset, or it has the capability of rewind the offset to read from history. So that is one of the advantage that we have in the Kafka compared to a queue. And consumer groups is an efficient way of reading from partitions, since the consumers in the group will distribute the load among them. Like in this configuration example, you need to define the group ID of each consumer in the consumer group before read messages. And first 2 consumers will read from partition 0 and 1, and the other consumer will read from partition 3 and 4. So if we add another consumer, it will be kind of a one-to-one mapping of consumer to partition. And we can add consumers more than the partition count that we have in the cluster. So the advantage is that in the event of consumer failure, the group will assign the load to an idle consumer. So let's see who managed the consumer assignments. We have 2 roles for this particular scenario, called group leader, who is the leader of the consumer group, and group coordinator, which is one of the brokers, get appointed as the coordinator. The group leader and group coordinator will rebalance the partition assignment in the event of consumer failure. To manage partition assignments, there are 2 proposals such as group membership protocol and client embedded protocol. The group membership protocol uses by group coordinator, who is in charge of the coordination of members within a consumer group. Client embedded protocol will assign topic partitions to members at client side within the consumer group. And these 2 protocols will rebalance the consumer group and partition assignment in the event of adding or removing consumers from the consumer group. And a special note is that there are no any writes allowed while the consumer group is getting rebalanced. And let's see how this rebalancing works. This is the workflow of adding a new consumer, which will initiate rebalancing. The new consumer will call for find coordinator on Kafka cluster to get the group coordinator, and it will call join group request on the coordinator. Then the coordinator will send list of active consumers and their current partition assignments to the leader of the consumer group. Then the consumer group leader will compute the partition assignments and send the proposed assignments in a sync group request. And in addition to that, all the other consumers also take part in sync group request, and ultimately all the consumers are getting their particular partition assignments as a result of sync group response. Then the continuous heartbeats will continue and the rebalance events are sent from the coordinator on the heartbeat response itself. However, there are some issues with offset commits from consumer when the rebalancing happens. For example, think we have one consumer and a new consumer is going to join the group. Then the rebalancing will occur. Let's detail out the real issue with an example. So the single consumer will be reading fourth record from the partition number 0 and second message from partition number 1, and the offsets which were read not yet committed. So while it is trying to commit the offset related to partition reads, let's say the rebalance happens, and once the rebalance happens, the partition assignment will get changed because there will be a new consumer who will be owning one of the partitions which is already read by existing consumer, and the offset which are not yet committed will not be able to get completed since the partition assignments are updated. So after rebalancing, the consumers will start from the last committed offset. So according to this example, none of the offsets are committed and it will start to read from 0th index. And this is what we call as duplicate reads. So on partition 0, record 0, 1, 2, 3 will read again, and on partition 1, record 0 and 1 will read again. So those are duplicate reads. So how can we avoid this? So to avoid this, we need to follow exactly once processing mechanism, which means we need to commit whatever the pending offsets before rebalancing is actually happens. The consumers can listen for consumer rebalance events, and in the event of rebalance, consumers should commit all the offsets which are pending to commit. And especially, as we checked before, all the reads will get paused while rebalancing is happening. And the other important thing is that the frequent rebalances will impact message processing performance because the rebalancing will delay processing of messages. So after rebalancing is happened, the group and the partition assignments will look like this. So the partition 0 will be assigned to one consumer and partition 1 will be assigned to the newly added consumer. So there are few important facts related to consuming messages. So we have the auto commit feature. With auto commit feature, consumer commit messages in equal intervals, and it is better to override auto commit and define your own commit strategy for better control. And the synchronous commits are blocking operations, and the offset commits should do in async and non-blocking for better performance. And you can use manual async commit with callbacks where the callback will execute the failure handling. So how that happens is the consumer commit the offset and hand over the error handling part to another function. Usually the async commits does not retry, because as per this example, if the first commit fails, the second one will contain the update of the failed commit. So we don't need to retry in async commit. However, the sync commit is recommended to be used in the event of error handling, like in a try catch block. Within the finally block, you should use sync commit in order to make sure that everything written up to the exception is occurred. So far we talked about cluster behavior, and let's talk about data communication into the cluster. So the producer uses a key and a value serializer since the data transmitted to Kafka is in the form of byte stream, and the consumer should use a compatible deserializer to get the actual data out from the message. And the serializers are defined with a particular schema. So as you can see here, in the schema we have error ID, error code, message, status and timestamp. And the same schema has to be used when the message is getting deserialized from the consumer end. And what if we need to update the schema? As in this example, let's say we remove the status and we make it like status code, and newly we will be adding trace ID. So then how deserialization should handle this situation? In the event of updating the schema, it will impact the existing consumers since the payload is getting updated. If the deserializer does not aware of those changes, and if it is a kind of a breaking change, the consumer will fail to compose the message correctly. So in order to avoid that, one approach is to send the schema along with the data within the same message. So the deserializer will know which schema to use in order to extract the actual data out. And to make this more efficient, there are tools available like Avro Protocol Buffer, which helps to maintain the schema as a kind of a remote service. And instead of embedding the entire schema within the message, it will allow you to embed only the schema ID within the payload. And this will be more maintainable, and at the same time it will reduce the size of the message. So as per this example, we do have 4568 schema, and as well as we have 3569 schema. So second one is the updated schema, and each producer will decide what is the schema that it is using, and the schema ID will be embedded within the respective message. And based on the schema ID, the consumer knows which schema to be used when deserializing the message. Let's talk about Kafka Streams. Kafka Streams allow to distribute events in a single topic into multiple other topics based on a particular condition. For example, as in here, if the messages need to split into regions based on a particular region parameter within the message, we could update them like this. So whatever the message arrives in all regions topic will get splitted into region 1 and region 2 based on the region ID attribute. We can use the Streams API to configure that, and whenever a particular message arrives in events all regions topic, it will get automatically populated onto region 1 and region 2 topics. Let's talk about what are the factors to be considered when we want to monitor a particular Kafka cluster. First thing is that if consumers are behind the partitions, it will make more time to read particular message. So the gap between publishing and consuming should be lesser. And if the partitions take more time to sync, there will be out of sync data in the cluster. And if the leader election happens frequently without adding or removing any brokers, and there should be something wrong with the cluster that you need to seriously focus on. Writing offsets should be efficient, else there will be duplicate reads if offsets are not properly committed. Related to hardware, keep constant monitoring on disk I/O since this is some sort of persistent operation. And Kafka is kind of a memory intensive program, and when the operating system is consuming swapping, which means dumping filled up data within the memory onto a disk space, will impact on application performance. And on CPU is not a kind of a critical factor, however it is recommended to use a particular dedicated CPU, otherwise you will be having delays due to context switching, because the CPU will try to consume requests of multiple applications at the same time. And you should watch for network spikes, because those network spikes could be due to unnecessary redirections, and those can reduce the performance of the cluster, and it is better to set up alerts on those. Finally, it is required to enable cluster JMX and consume cluster events via a particular monitoring tool in order to watch any particular issues with the cluster. Finally, there are some popular tools available to watch Kafka cluster topics, partitions and cluster details. So those tools are like Kafka Manager from Yahoo and Confluent Control Center, Cloudera, Lenses, Datadog, Kafdrop like tools. But for this example, I will be consuming Kafka Manager from Yahoo in order to demonstrate my implementation. Let's check out the design implementation related to this. This is an extension of previous project. So we discussed about the car microservice, trip microservice, and couple of best practices that we can follow in there. And my fleet config server is the Spring Cloud configuration server that I use to separate configuration from all the microservices. And myfleet configs is the Git repository where I use to separate all the configuration from the code. And there is one utility file as I mentioned during talking about the theories, so it is better to remove the boilerplate code from the microservices, and the producer, validators, and there are a couple of other things are separated out from the code into those repositories like in utils and the validators, and I have covered those in a couple of previous other videos, and if you want to check you can go and check them out. And related to this video, I will show the analytics configuration of the Kafka appender. So Spring Boot by default coming with the logback, and first we need to exclude the logback which is in the default logging starter pack, and then we need to add the log4j2 as the dependency, and then we need to configure the log4j2 configuration. And according to log4j2 configuration, I have defined the root level logger as the async appender Kafka, and I have defined the error level as info, and if I go to async appender Kafka, it is defined as a kind of a async block. So this is how we can achieve the async behavior in Log4j, and whatever the appender that I wanted to execute in async mode, I need to define in here. So there are other configuration that you need to define with the async to define the length of the buffer, but I am using default behavior since this is a kind of a demo. So then we can use a Kafka appender here. So in the appender, I need to mention what is the topic that I wanted to push the messages, and the message pattern layout has to be defined here, and I need to define what are the bootstrap servers of Kafka. So list of servers I need to define. So the appender will be talking to one of the servers, then it will be able to identify where the topic is, and it will be writing the message accordingly. And there are other functions like failovers. You can use failovers in Log4j if you want, but my scope is mainly related to asynchronous Kafka appender in this example. So if I go into one of the services, I can create a logger factory. So this is a SLF4j logger. So when it is running from the class path, it will be identifying the log4j2 dependency, and then on logger I can define whatever the messages that I wanted to define, like info, error. Then the message logging will happen according to this configuration. So the root level logger is the Kafka appender, so then it will be sending all the messages directly to Kafka in a async mode. So it will be consuming the default data buffer, and from this topic I can consume the messages, and I can pull those messages onto Logstash. Let's talk about the other path, the direct message publishing. So as we talked earlier regarding exception handling, all the control level exception handling are splitted into exception advices. So you don't need to write bulk error handling code within the controller. So then all the exceptions are handled within exception advice, and using Spring AoP there are point cuts defined in order to capture the message, and I have auto-wired the exception messenger here. So the exception messenger is actually implemented in the utilities. I will show it later. So I will be simply calling the publish message with the error ID exception log into the publish message method. And if you want to get an idea how this logging framework works, then you can watch my one of the previous video regarding how the error handling should be done in enterprise grade microservices. And if I go to the exception messenger implementation, it is implemented within the utilities, and this is implemented on producer API, and I have the publish message here, and I have defined the Kafka topic that I wanted to push the message, and I need to define the bootstrap servers and the level of acknowledgement from the producer in, and the retries, and the batch size, memory, serializer, and the deserializer we need to define as I mentioned. And according to this example, my key and the value will be just plain strings, and this will be submitting the message into Kafka directly. And this code is splitted out from the microservices, so we can publish it to a kind of a repository server. But for demo purpose, I have defined it in the Maven POM file-based dependency. But in real production environment, we need to define all those dependencies in a repository manager, and the POM should be authenticated with the repository manager to import necessary dependencies. And regarding the streams, so this is my streams API implementation. I have a simple logic here. So what this code will be doing is, from the Kafka stream, I will be reading the message. So this first string is for the key and the second one is for value, and this is the input, and the second one is for output. So my input and output key value pairs will be same. Only thing what I will be doing is, based on this particular error code, I will be splitting data. So all those configurations can be defined in a configuration file like this. You can use either YAML configuration or properties based configuration. So I need to define one of the brokers here. You can define list of brokers here, and I need to define to which method this particular configuration should apply, and I need to define in topic. So I am reading from my fleet user error log topic, and I need to define the output topic as well, my fleet SC data error log. So this is my target error log, and I need to define a deserializer for the in topic since I am reading data from it, and I need to define serializer for out topic since I need to serialize and send messages to out topic. And when you are using configurable Streams API, it is a lot more easier. It will reduce the coding drastically. And this is my Kafka configuration. I need to define a broker ID, and then I need to define the listeners for my ID, the IP address and the port, and I need to define the advertised listener, so the other brokers will be able to discover my broker with the advertised listener, and we leave other configuration as default, and at the end we need to define the Zookeeper connection. As I mentioned, we can give the Zookeeper ensemble in here for the brokers to communicate with Zookeeper. As I talked about, so this is the Zookeeper configuration. We have the tick time and the data directory, client port, init limit, sync limit, and so this is the Zookeeper ensemble. And I can start the Zookeeper like this, and the Kafka server also could be started with the Kafka server shell, and you need to define the property file. So the Zookeeper and the Kafka broker is up and running, and I do have another two physical implementations of that, as you can see in this screen. So those are the configurations of other two instances. So we have started the Kafka cluster. Now let's go and start the Spring configuration server first. And I have demonstrated this in one of the earlier messages related to exception handling. You can check further details there. And I have two microservices. Let's start the trips microservice like this. And let's start the car microservice. This is a Kafka consumer which will be consuming the messages from the analytics topic and publishing those data onto a MongoDB for demonstration purpose. And finally, this is my Streams API implementation. So according to the design, I have my trip microservice up and running and cars microservice up and running, and the Kafka cluster is up and running, and this is where the demo consumer is starting up, and it will be publishing data into MongoDB, and this is where my Streams API is configured, and all the messages related to this particular error code will be pushed into this particular topic. So my entire setup is up and running. So let's create a console consumer to see the content of this particular topic, and I'll show the content of this MongoDB once after the events are pushed. And let's define a command line consumer like this, Kafka console consumer, and you need to define the bootstrap server, and we can define the topic name like this, and it is up and running for the topic which is populated by Streams API. And I'm using Postman for this. Let's say I want to post this particular message, and according to this implementation which I have already discussed in one of the previous example, this will be looking for this car registration number. So it is not available at the service level, so the service level validation will be failing. It will be generating a kind of a user error. So if I execute this, so as you can see, this is the error generated with this particular error ID. And if I go into MongoDB, it should have this particular record reported. If I go into the latest record in the MongoDB, you can see this is the error ID which I have generated, and this is the error message, and the details are published into MongoDB. And if I look into the console consumers, this is the error message recorded at the myfleet user error log, and you can see it is filtering the defined error code, and it is pushing the error message into the myfleet SC data error log. So this is through the Streams API that I have defined. And as I have mentioned, I am using a Yahoo Kafka manager, and in the Yahoo Kafka manager I need to select what is the cluster that I want to check. So I have created this cluster, and I have 12 topics, and I have 2 active brokers. And if I go into the brokers, it will be showing the ID, host, and the port, and the JMX port I have not configured. And if you want to use it for instrumentation, as I have mentioned, you can use it, and you can see all the topics and their usage details like this. So there are a lot of other tools available, as I have mentioned earlier, so it's better to use this sort of tool to check the health of the Kafka cluster. And I will mention links to these code repositories and step-by-step guide how you can set up those in your local environment, and you can try those out. I hope this content is fruitful for you, and all the links related to this video are mentioned in the description section below. And please make sure your post notifications are on, and let's meet again in another interesting topic like this. Until then, stay safe.